Okay, so let's get rolling. As I said in the, I don't remember if it was an announcement or an email, whatever I sent, we're putting a pin in our game for a second because we have to look at two-dimensional arrays, and it's going to be easier to talk about them initially in a different game. So we are going to create another game in Unity. This one, I guess, a little bit less geeky, but still a whatever. How many of you are familiar with the game Connect 4? Is that something people still play? That's still a thing? All right. Well, all right. So we are going to be creating our own version of the game Connect 4. Um, just awesome. So, we're going to have something that'll look something like this, where we drop our uh, things in, trying to get four in a row. But before we get the visual side of it, we have to think about the data structures we're going to build underneath the hood to represent this. Yeah. Yeah, everything went fine. Thank you. Late that same day, it was outpatient, but I should have taken some video of how loopy she was. It was very disappointed in myself that I didn't do that. It was one of those things. Oh, I'm out of time. It was one of those things where uh, on the way home, we were about 10 minutes from the house. She asked the same questions like 20, 30 times. Seemed to be very concerned where her purse was. It was a dental thing. So, yeah, basically the same thing. But she has to be under significant sedation with her anxiety. So, I really missed an opportunity to record that. Yeah, I know. I'm disappointed in myself. That's a. uh, so, in any case, we want to start thinking about representing a two-dimensional grid. And we do this through we've talked about arrays up to this point. And so we have a decent idea on what an array is in terms of its pros and cons. If we know the exact size of something, an array makes a lot of sense. If we know we need to hold on to 100 elements, for example. While sure, we can create other list data structures that allow us to start off with nothing and then grow it arbitrarily. But if we know exactly how many things we're going to hold, we're not going to get as fast as an array. An array is the right tool for the job. And the reason I'm kind of harping on that idea here is that I don't want us to look at arrays as being the old way of doing things, and then things like lists or array lists, whatever, as the new way of doing things. That's not an accurate representation. Go
So
ahead.
you're saying that like both are useful?
100%. Yeah, I mean, arrays are used all over the place. Even today, just whenever it ultimately comes down to using the right tool for the job. So whenever you run into a situation where you need to store some stuff, you might initially ask yourself, well, how many things am I going to store? If you can answer that question with a finite number, like I'm going to store 30, pretty much you're going to use an array. If you are going to say, well, I don't know how many things I'm going to store, like at least 10, then you start leaning into this idea of maybe creating a list type data structure for storing those things. Um, the list is lower performance, doesn't move as quick, even though we probably wouldn't notice because it's still going to be really fast for a computer. So unless you're doing a very specific task where it's doing something so often that you start feeling the time, you probably wouldn't notice a difference. But um, right tool for the job is probably the best way to think about it. All right, so I'm actually going to bounce back here to an older. Is this? I want to get back to when we first talked about. I'm going to end up flying all the way back. So let's just draw another picture here. If we remember correctly about original arrays, when we first talked about these, let me hide this. I had something that looked kind of like this. How many rows and columns is connect for? 6 by 7 or something like that, I think. 1, 2, 3, 4, 5, 6, 7 by 1, 2, 3, 4, 5, 6. Oh, okay. Well, I counted on the board. Wanted to go right to the. All right, so we need 7 columns. The who, what? Yeah, yeah. We're you could take any board game that's like this and take a very similar approach to what we're going to do here. All right, so before we build the rows aspect of this, let's remind ourselves how these arrays work. So the syntax is almost identical in C sharp. So let's just go with the syntax we've already been exposed to. So I'm going to say we have an int array. AR is equal to a new int array of size 7. All right, so that might be the syntax we use to create that thing up on the top. So what's the value of AR? What kind of value is stored inside of AR? Cat, dog, or memory address? All right, so how do we know that new keyword should kind of throw up a red flag that we're probably going to be getting some memory stuff? All right, so AR is going to be some memory address. I'm going to represent it up here. Just reminding us how these arrays work. Bounce it down here. So remember, arrays are 0 indexed. So this is bucket 0, bucket 1, bucket 2, bucket 3. All right. Now let's just say to keep our stuff easy here, that AR ends up getting memory address 100. So this would be like 0x, something like that. The memory address 100. All right. I made it look like a memory addressy thing, but it's just the number 100. All right. So I'm going to go ahead and write 100 here. All right. Now, when I say something like AR at bucket 2, what is that memory address? So if AR holds the memory address 100, what's the memory address of AR at bucket 2? And how do you know? This is review, but we're jumping back into the memory pool, which is an uncomfortable place for us to be swimming, right? Okay, but we want to hit it again because now you're more mature programmers and maybe it'll make more sense now. Go ahead.
AR 0.00.
There. Let me just put it at 100. Let's not focus on the hex part of it. So go ahead. Okay. So she says that this is going to be 102. Is that what you're saying? Yeah. Okay. Which presumes this would then be 101. Okay. So how did you come up with the 102?
The address for 0 was 100, so 0 was 100, 1 was 101, 2 was 100.
What kinds of values am I storing in here? Integers. How big are integers? What if you got a container that's the perfect size for holding an int? How big does that container need to be?
Big enough to like hold the number. It could be 256 bits.
Integers are set size. So integers are 32-bit values. 32-bit values. Remember the negative 2.1 billion to positive 2.1 billion? That's the range of values that will fit inside of an int primitive type. All right, so these are 32 bits or 4 bytes. So what you gave me here, yep, counting by fours. So this would be 108. Yep, yep. So great idea. Your answer would have been right if I was storing chars. Chars are actually your answer would have been right if we were storing chars in C++. It would have been still wrong if we were storing chars in Java or C sharp. Why is that? Why are chars different in C++ versus Java and C sharp? Remind me, I forgot. Got that, Mar. Fight over it. Go. There we go. You. Chars still exist. It's how they're represented under the hood that was replaced. So in C and C++, a char is represented as an 8-bit value because it's using ASCII, American Standard Code for Information Interchange, whereas which has 256 unique characters. That's an ASCII lookup table. Whereas in newer languages like Java and C sharp, a char is actually represented as a 16-bit unsigned value, 0 to 65,535. So to give us 65,536 unique representations. So we have this lookup table called the Unicode lookup table, which has more than just the English alphabet and smiley faces in it. Okay. But at the end of the day, a char is a char from our perspective. And since we're all speaking English, we probably aren't going to get into the Unicode stuff, but it makes sense that, in fact, I think I showed everybody my Coin a Greek app. Yeah, if we didn't have Unicode, that would have been problematic because the Greek alphabet is outside, unless it has math stuff. I don't think the Greek alphabet's in ASCII, but in any case, potentially could have been problematic. All right. So since we are storing integers here, an integer is 4 bytes big, or 32 bits. Therefore, the size steps we take through memory are integer size steps or 4-byte steps. So bucket 2 is that memory address 108. How did we get that? So when we say AR at bucket 2, we're actually saying AR plus 2 times size of int, which is the base address of AR is 100 plus 2 times 4 for size of int is 8 equals 108. What about AR at bucket 0? AR at bucket 0 is equal to 100, the base address, plus 0 times 4, which is equal to 100. So on and so forth. This is how arrays work. We're also reminding ourselves here that this is also the limitation of arrays. This is why we have to choose the right tool for the job. If we know exactly how many things we're going to store, an array is the right choice. Otherwise, we're blocking off a piece of land that we either won't fill or is going to need to hold more stuff later. So we're going to have to destroy this and go and waste that memory and go build new memory and copy everything over. So arrays are a great tool when we know exactly the number of things we're going to store, which is the case here since we know how big the board is. All right, so that's what an array is. Now, what about a two-dimensional array? I'm going to go ahead and just steal this guy. So a two-dimensional array is an array of what? We want to think about the kinds of values we're holding. A two-dimensional array is implemented in terms of a normal array. So a two-dimensional array is an array of arrays. So if I say something like, I'm on the second one. So this would be int array, AR is equal to a new, what do we say? 6 rows by 7 columns. Like that. So now we're representing that. Now I'm going to go ahead and gut this a little bit. Are we all on the same page now that this is the memory address AR at bucket 0 0 gives us maps to that memory address, 2 maps to that memory address. So typically when we're thinking about arrays, we're not really thinking about the memory addresses at all. We want to appreciate as programmers that that's what's happening under the hood, but that's all managed for us. So really we're saying, hey, I got a bunch of things I want to store. They're indexed starting at bucket 0. All right, so I'm going to go ahead and dump this part. All right. I'm just going to scooch that over. All right. So now, if each of these buckets are holding on to an array, let's think about this in C++ terms. That way we can wrap our mind around it, even though in our newer languages like Java and C#, it gets abstracted from us a little bit. Remember in C++, an array was, if we had an integer array, we could have written this a little differently. Let me actually just go back to this one real quick. In C++, we could have written this as int pointer AR is equal to malloc 7 times. Actually, we would just say malloc 7 since it already gets us the size of this. So this would get us enough memory to hold this many of these guys, storing it in a pointer, a variable built for holding a memory address. All right. We've seen this happen in Java. We've seen it happen in C#. I may not have actually shown you in C#, but it's identical to Java. That if we were to create an array and then print out the value of AR, we get a memory addressy thingy. All right. Just like if we used the predecessor to the new keyword and we used the memory allocate function in C and C++, malloc, we're saying, I want 7 of these guys, give me enough memory for that. Same job the new keyword's doing. All right. But if we're creating 2-dimensional arrays, we'd use a syntax like this, where we're saying, look, I want an array of arrays, 2-dimensional array, where there's 6 rows and 7 columns. We are the ones who are actually giving meaning to rows and columns in this case. We're just saying the 6 part of it is the number of rows. The 7 part of this is going to be the number of columns. And as long as we stick to that organization and how we're calling it, we're representing the thing we want to represent. Similarly, nothing prevents us from creating a 3-dimensional array, where now we're representing basically a cube, right? And if we go 4 dimensions, then the world folds in on itself. So never try to compile that. Well, I guess maybe. All right. So when we think about a 2-dimensional array, I want us to think about this as being an array of arrays. We're going to visualize it because we're trying to make a grid, right? I mean, at the end of the day, we're trying to represent the Connect 4 board, and in our minds, and in the minds of any programmer that's already learned what's happening under the hood, we're just thinking about this as a grid, rows by columns. This whole memory stuff that's involved here is interesting, but really unimportant for working with it, even though we are going to talk about it for a little bit here. All right, so then we're going to have 6 of these rows, right? All right, so that's kind of what we're trying to create, is something like that. All right. Now, when we create this guy here, we're thinking about it in terms of this, but what's actually being built move the rest of these down. Think of each of these guys as its own array. Doesn't matter that we've depicted it as going vertically. It's an array. This is an array of 6 elements. This is an array of 6 elements, so on and so forth. This guy here, each bucket of this array points to the beginning of each of the other arrays. All right. So effectively, we have an array of integer pointers where each of those memory addresses point to the beginning of this array. Bucket 1 points to the beginning of this array. Bucket 2 points to the beginning of this array, so on and so forth. Okay, that's what an array of arrays actually is. Okay, when we resolve it, when we say, okay, I want to go to AR at row 2, column 4. We're going to say go to 0, 1, 2, go to column 0, 1, 2, 3, 4. That guy right there. We're thinking about it like a grid, but under the hood, when we say, I want to go to that particular, really the way I'm arguing about this, this thing should be laying on its side. I don't know if there's a good way of me doing that. Let's do a gesture thing. Super Ninja? Nope. Imagine it's laying on its side, doesn't really matter, but same thing works out here. If we want to think about this in rows, we can say that this would actually be the rows versus columns. Again, this doesn't matter, but when we say we want AR at bucket 2, the way we would probably think about this is, give me, we already had 7 up there. Let's turn that into the 6. And turn each of these into the 7. And we'll make those green. You didn't move all those at once? Poor design. That was going to be epic. All right. All right. So now you can imagine this laying on its side where we have our rows by column. So when we say go to bucket 2, this is bucket 0, bucket 1, bucket 2, bucket 3, bucket 4, bucket 5. So 6 rows by 7 columns. So when I say 2, bucket 4, I'm going to say go to bucket 2 of my rows, and it points to my 7-element array that holds the columns. All right. So that's what's ultimately happening here, even though we can just think of this as row 2, column 4. We don't need to think about the memory when we're actually implementing this thing, but we want to understand what's happening under the hood. The point of this is that 2-dimensional arrays are not different than 1-dimensional arrays. An array, a 1-dimensional array can hold anything that we can create types of. So we can have an array of ints. We can have an array of chars. We can have an array of pointers, where each of those pointers points to the beginning of something else. Pointers could be an array. Pointers could be, we could have an array of players, which is an array of memory addresses which points to a player object. We want to think about this in terms of our current game, our dungeon crawler. So objects are memory addresses, and we can have a collection of those. So two-dimensional, three-dimensional, four-dimensional arrays are nothing special. They're not like special implementations. It just changes the thing that lives at each bucket. We're always working with a one-dimensional array, but sometimes the things that live at each of those buckets allow us to transport ourselves to another place in memory that has stuff in it. Now, with that in mind, if AR has a base address of 100 here, there we go. So let's just use that example. If AR has a base address of 100 here, that means this is 100. What's the memory address of this? Bucket 1 or bucket 2, if the base address is 100. Bucket 1 will be 100 plus the size of a pointer. So depending on the operating system you're on, a pointer could be 32 bits, could be 64 bits. Most of our modern operating systems, when you think about pointers, they're going to be 48-bit pointers. I think we mentioned that in class, even though all our operating systems today are 64-bit operating systems. What it does is it holds back 16 bits for super user space. Memory addresses specifically owned by the operating system that users, our programs, don't get to access. And then they give us the rest of the bits, 48 bits, to represent our stuff. So we get 2 to the 48th unique places we can put things in our computer. All right, so if this was memory address 100, this would be 100 plus 48 bits plus 48 bits plus 48 bits for the different memory addresses, because that's how big a memory address is. All right, but again, we don't care how big of the steps we take through memory. We just can think of this as this is row 0, this is row 1, row 2, row 3. It's going to live where it's going to live. But in this particular case, there is no guarantee that that array that I have highlighted there. So bucket 0 here is going to hold a memory address. So let's assume that this holds the memory address 150. So that means it's pointing in memory to memory address 150 where this array lives. This guy here does not need to hold the next memory address over. He lives at the next memory address over. But just like we had back here, there is a difference between the value that's stored in a particular bucket. Why can't I? Oh, I did it. So here, I'm going to put a 5 there. Notice that 100 is the location in memory where this bucket lives. That bucket holds a value. In this case, the value I put in there is a 5. And the way we access that bucket in our programs is by giving it the index of the bucket we're interested in, which is bucket 0. So instead of us passing in saying, I want the thing at memory address 100, we're just saying, hey, look, give me AR at bucket 0, and you figure out where that lives. We're leaving that up to the operating system to do that math for us. All right, but what I want us to see right here is there are 3 different values we're working with here. One is the 0-based index. One is the whatever the base memory address is of the array. And the other one is the stuff the array actually holds. So if we go back to our 2-dimensional array here, let's see if I can shift everything down. That good enough? Yeah, I did it in red. So this could be 100. Um, 6, 112, 118, 124, 130. So that's the memory addresses where these particular buckets live, because we're taking 48-bit steps or 6-byte steps through memory to hold memory addresses. But each of those holds a value. So in my example here, the value that this first one holds is the memory address 150, which is a little dangerous because that's actually a little bit farther, but technically not in conflict. So we're okay here. So let's say this is memory address 150. There isn't any guarantee that the guy next to it will have the next logical memory address. This might be memory address 400. This might be memory address 500, 900, 990, let's say, 1140. So each of those buckets is holding on to a value. The value that lives there is a memory address, which points to the beginning of the array that that guy points to. And those guys don't need to be in any sort of order. Yet, if this is 150 and we're holding on to a bunch of integers, that means that this guy lives at memory address 150. This guy lives at 154. Actually, well, that's 154, 158. Actually, we're doing this a little funky, but that's fine. Math works out. All right. 166, so on and so forth. This one would be 400, 404, 408, so on and so forth. 500, 504, this would be 900, 904, 990, 994, 1140, 1144, so on and so forth. All right. So as far as our computer is concerned, this array right here has nothing to do with this array right here in terms of where it lives relative to its neighbor. Because the beginning, the base address of this array is stored at bucket 0 of this array. The base address of this array is stored at bucket 1 of this array, so on and so forth. But within each of these arrays, they will be in contiguous memory, memory right next to each other. Just as here, these guys are in contiguous memory, memory right next to each other. So a two-dimensional array is a one-dimensional array with each bucket pointing to another completely independent array that lives somewhere in memory, but all the elements of that array are contiguous in memory next to each other. All right, so that's what's happening under the hood here. Questions about this before we start using two-dimensional arrays and moving away from the memory under the hood, because really it's not our problem. When we create it, it creates the memory, and then we just use it. We say, go to row 2, column 4. Go. All right. So we want to represent this guy as our game. And we decided, so I'm going to go back to representing this as rows and columns, the way we think about rows and columns. Steal that guy there. Our 7th column back on. Okay. That's a tic-tac-toe board from from our perspective. All right. Um, this is column 0, 1, 2, 3, 4, 5, 6, and these are the rows. But when we play tic-tac-toe, we don't really think about the rows when we're playing, right? We just drop a checker in and it falls as far as it can fall. Good. Sorry, connect four. Yeah, you have to resolve my memory addresses. When I say one thing, you have to resolve what I actually meant. You got to follow the pointer from tic-tac-toe. A normal amount. Yeah, this is just old. That's what we're dealing with here. All right. So this is our Connect Four board. And when we're playing Connect Four, the idea is we're always picking a column where something drops into. And the checker falls as far down that column as it possibly can, either hitting the bottom or landing on top of whatever checkers were previously there. We're going to be able to use Unity's collision detection and stuff like that to handle that for us. So we get the visual mechanics of our board completely through Unity. Yet we're still going to have to keep track of after each move when we try to say, is there a winner? Does somebody have some number of, do they have four in a row, either horizontal, vertical, or diagonally? That's when we're going to have to be doing the math under the hood using a two-dimensional array that represents what we're visually representing here. Does that make some sense? All right. So we want to start thinking about how we're going to represent that in Unity. But before we get to that, well, I'll start messing with that here, but then we want to start thinking about where things live and thinking about the objects we're going to have that we're going to be working with here. So I'll go into create a new project. So we're inside Unity, create a new project. We're going to call this guy Connect 4. Let's see, where is it storing this? Okay, that's fine. Put it someplace where you can find it. I'll use the universal 3D core thing, the same thing we've done before. I'll say create project. It's going to give us our basic scene that just has the camera and a light. So what we can do is we can create a thing along the bottom. If you remember, like in Connect 4, it has a little slider that lets the things fall all the way through or whatever. So we're going to create a base at the bottom. This is global volume thing. I don't remember that guy from before, but whatever. It's probably a new thing. All right, so I'm going to go ahead and I'm going to create a 3D object. I'll create a cube. So there's that guy there. Actually, we'll put him at 0, 0. And we'll stretch him out. So let's see. Let's just do the scale. We'll do one per, and let's just see what that looks like. So we want it to be on the X7. Have the right thing selected. On the X7, the Y will keep at 1, whatever. Z will keep at 1 for right now. I want to look at this thing dead on. Let's see. Yeah. So we have Y going up, X going to the side. So I think this is looking at it directly on. I will just lower this guy for right now. All right. We want to have something that can drop down onto this and stop. All right. So let's go ahead and let's create a 3D sphere. Cylinder actually might look more like a checker if we make it thin. So we'll create a cylinder. Right, and we'll go ahead and rotate that guy. Where's my whatever. My cylinder, we'll rotate it. We're rotating it about the X. Right? And we probably want its scale on the Z to be like 0.001 or call it 0.1. Thinking about this the right way, aren't I? Why did it get so skinny? Because this is its, well, whatever. All right, so there we have our checker. We want this guy to be able to fall down. And so we see we kind of have it, it looks like it's hitting in the right spot. All right, so we'll put it up there for right now. We can always give them colors or whatever. All right, so we want this guy to be able to fall down and hit the thing underneath it. So that means we're going to have to allow gravity to impact this dude. How do we let gravity impact a game object? Go ahead. Yep, rigid body. So we're going to make this guy a rigid body. And make sure we go down to rigid body here and you have the little use gravity thing check boxed. So now when we run this, we see the thing fall out of the sky. Oh, that's what, so I did have it backwards. But just so we're looking at this the right way. There we go. All right. So the rigid body allowed us to have gravity impact this guy, but what allowed them to hit each other? Our capsule here has a capsule collider. Our sphere here, or our box here has a box collider. Colliders interact with each other and prevent things from going through. If we turn off our box collider down there, and then we run it again, we'll see our dude falls right through. All right. So we could use this to effectively create our game, right? You know, we can build out a kind of a grid so we see the things falling down through the little slots, that type of thing. So what we'll do for our homework next class, and I'll put it up, is you build your own version of what the game board looks like. We're not putting any logic into it yet. Just drop things in. Keep in mind that, you know, once something lands, I'm going to create another one of these guys. They land on top of each other. You can give them some colors, whatever you want. Just build your design of what your board looks like. All right, questions about that? Not a hard coding thing, just the design. Go ahead. It's on both. It's on the cylinder. Oh, the rigid body is on my cylinders, my coins that I'm going to drop down. So anything I want gravity to impact. Oh, I got you. So when you select your dude down here at the bottom, I added component and search for rigid body. Yep. Just make sure you hit the checkbox for gravity. Because if you don't hit gravity for that dude, if I turn gravity off there, then the second one won't fall. First one, it's the old water slide technique my brother and I used to do. He would stop halfway down and I would come plowing through. All right. So in our last couple minutes here, let me go and we want to start thinking about how are we going to represent our game board. All right, not visually, programmatically, because we're doing something very similar to what we did in our dungeon crawler, where we have this visual representation of our rooms, and that guy just always looks the same way as our data structures say it should look. All right. So if we start planning this out, Connect 4, we're going to have a board. Okay. And a board is going to have a 6-row by 7-column array representing our game board. We also are going to have checkers. We're trying to represent the thing. So we'll have checker objects. Checker has a color. In the traditional game, it's red and black, right? So a checker will have a color. So when we're actually doing the looking for a winner, we're going to be looking for 4 in a row of the same color. All right, so that'll be our checker. Then we're going to have maybe a game manager. So this is the guy who actually plays the game for us. So he will house the board. So holds a board and applies the rules to the game. So these are the objects we're going to have to build in order to do this. And then we create that game manager is also going to have it, go back and forth between whose turn it is. All right. We can build AI into our thing. And initially it's probably going to be really crappy AI. Instead of trying to detect when the player is about to win. We can just have it randomly pick a column that has at least one spot open. So hopefully we don't lose to our AI very often. All right. So all of these are going to be non-mono behaviors. These are just normal plain Jane objects that we're going to be building. All right. So, as I said, for next time, homework, create a new Unity project for Connect 4. Represent your game board however you want. I guess just submit a screenshot. Of your game board. Test it by having things drop down like we have currently. All right. All right. So next time we'll come back. We're going to start writing our objects. We'll create our scripts folder here, start putting our objects in there and having them work with each other. All right. Questions, comments, concerns, bribes. All right. I will see everybody on Wednesday. Turn my gravity back on here. All right, back in business.
There's a simple way to pretty much add a setting effect to things. Because like right now they pretty much just they all in the instant stop.
I think there is actually a little bit of a bounce. Yeah, the top one bounced a little bit. So that has to do with when we click on this guy. I think it's the mass. Yeah, if you make the bottom guy, so that's my bottom guy. Let's make the mass 100. I think you'll get a little bit more pop. Oh no, that was.
Oh wait, less mass. Since then it would be lighter.
Yeah.
So right now you're like putting down the wall.
So here we'll. There we go. Yeah, so you can mess around with mass to get that effect.
Okay, because I know one of the satisfying things for me with Connect 4 is the fact that they always bounce like.
Oh, I see.
Part of the charm. Anyways, have a good
You could also give gravity effect a little bit more. You could increase the mass of the thing on top so it falls quicker. at least initially until you hit terminal velocity. But I don't think it's falling enough to hit terminal velocity. So you can mess with it to get your look you're going for.
Yeah, but yeah, also if you start up higher, then yeah, the kickball speed. So
It's true. Just have a drop in from above. We have our checkers just staged like 100 feet in the air. And as soon as you pick your column, you can even have flames coming out of the back of it.
yeah, honestly, just have like maybe just even have like an aircraft thing.
Yeah.
Just a plane just flies over and your checker.
Yeah, and plane, or I'm sorry, flames wouldn't even be that hard. You would add a particle system to it. So you could have it just start spitting out particles in a certain direction and then turn it off on impact.
Oh, there is so much. I think I'm going to.
Well, good.
Have a good day.
Yep. Later.